Today we start the section of our course in which we will study the possible molecules that we can use for building our nano devices for sensing or for nano and molecular electronics. We will start with two lessons in which we will analyze the conductive molecules. My first lecture will start with an introduction and a recover of some concepts that were explained in the previous lecture from Professor Piccinini. And we will talk about, again, the metal structure. And then we spend some words talking about the contacts, and we will talk about nano gaps and about these contacts with the nano distance will be also a matter of laboratory that we will do later. Then we will go deeply in understanding which of the molecules we could need for our application, and mainly we will talk about organic molecules, so the hydrocarbons, in particular benzene, and we will see how we can take these molecules for building molecular wires. Then the end of this first lecture will be focused on analyzing the different families that are now used in literature and the applications. Well, I want to add some points that were already touched by Professor Piccinini, why we need to put together electronics and molecules. From an application point of view, one of the first interesting points is that we can produce them at a low cost. Low cost means that now we are in the step of the development of this application that is related to research. So it is correct to say now that the applications, the devices we develop now are prototypes, but the technologies that we use, the processes that we use are simple at the end, and so it is true to say, and it's possible to say now, that when we will reach a final device, it will be applicable using simple, not too many processes, not too many complex processes, and so it means that they can be produced in a low-cost way. The application of electronics plus molecules are several. We can talk about electronics, optics, already the OLED are already in the market, and also sensing. The technologies that we will see are derived by the standard microelectronics technologies, because it is a perfect choice to take the already well-known microelectronics applications to be used as interface to contact and to manage the information that you have from your nano device. And it's clear that one of the great advantages is that we are talking about nano dimensions, so we reduce our dimensions. And this was a concept already touched by Professor Piccinini. We must think that it's important that we lose maybe and try to forget something about the old, I can say, applications based on gating, based on transistor concepts. They are important, of course, we must continue to think about them. But we are opening, and now it's open, a new possibility using nano dimensions, and so the effects in physics that these nanodimensions have as impact in the properties, in the functionalities that we can obtain. So it's time also to think, to set up completely new ideas, completely new structures. For understanding with the topics in which I want to go in details today, we have to consider mainly 4 steps and 4 things that we have to exploit and to study. First of all, you already start in the previous lectures to study which are the basic principles that leads and generates inside a structure the molecular conduction. Then we must decide which are the good molecules for us for building molecular wires. And then is important, and I will push on this concept, the importance of the contacts, and so to study and to try to find good solutions for building effective contacts for our molecules. And last but not least, all the studies and the analysis related to the simulation that help us in understanding better what is happening in our nano device. We start from a structure that you already know, so the metal molecule metal structure, because this is the brick that we need to set up for building, we can say, our house, in which we will develop our sensors, our new nanoelectronic and molecular electronic devices. This slide is well known to you because you already had it in the previous lectures from Professor Piccinini, and you see, now I want to recall the basic concepts that are useful for us to continue and to apply them for creating molecular wires and molecular devices. You remember that this structure is based on 2 metal electrodes. One can be considered the donor, the other can be considered the acceptor, and in the middle you put your molecule. At the equilibrium, you have all the energy levels, the electrochemical potential, mu1 and mu2, the Fermi levels that are all at the same level, and so in this case, at the equilibrium, you do not have a current inside your structure. But one of the first important points that we have to touch is what is related to the gamma that you consider, that was defined before using a tau, so the h bar on gamma is the time that the electron needs to pass in the interface molecule metal. I took these slides from NanoHub. It's a very interesting website, so I suggest you to deep inside it, where Professor Datta used also this concept, so the reverse of, the inverse of what Piccinini called the tau is the gamma on h bar, that if it was the time to pass, it becomes a rate, so it becomes what is named the escape rate, gamma on h bar, of the electrons inside our structures. I show you this now because this gamma will be one of the key points for having and obtaining the currents, and that will be one of the parameters who will give us the numbers, give us how the conductance and of course the current will behave inside our structure. You know that for inducing a current inside the MMM structure, you must move the level of the mu's. In this case, we are applying a negative voltage to the right electrodes, so applying a negative voltage, the mu level goes up, and in this case, we have the first simple example that if the energy level, one of the free energy levels of the molecule, it is inside the levels mu1 and mu2, in this case, we start, you see here, to have a current. This is a very simplified model, just to start to understand what's happening. You know that after it, we must consider that in the structure, the model and the situation is more complex. So we have a broadening of the energy levels. And about this broadening of the energy levels, I want to put my finger on these two equations that give us the possibility later to use them for understanding the current and the conductance in our molecules and devices. The first, this one, says us what I already started to tell you. You see, in this equation, we have that our current is related to the states that we have in our molecule, to the gammas of the two contacts, and the difference of the Fermi levels of the two metal electrodes. What I want to point you out is that you see that the current, it depends directly to the gammas. So it depends directly to the quality of the contacts. It depends directly to how you build and you create your contacts. The second equation on which I want to do some comments is that becomes from Landauer studies. Here you see that Professor Piccinini introduced you the transmission spectrum that is related to the probability to have a transmitted electrode between the two electrodes. And in this case, you see that the current is proportional to the integral of the transmission spectrum. We will see integral means area. So studying some areas, and we will do it later, we will have also an idea and a direct information of how much is the current inside our structure. Last thing that I want to recover and recall from what you did before is that applying all the equation I show you, you obtain what is named the quantum conductance. That is a term that becomes from 2q squared to h, that if we do a calculation has a value of 77.6 microsiemens, that means a resistance of about 13 kilohms, 12.88. This is the basic conductance that you have in case you have your last, we can say, molecule inside your electrodes, and so we will use this in the lab when we will build the nano gap inside a wire, because if we reach this value, means that we reached the last possibility to have something that interconnects the two electrodes. And so it's a sort of threshold. After it means that if we break it, we put out the last molecule inside our electrodes, and so it means that we create our gap. We are talking about, already started to talk about nanogaps, just a few words about them, because now it is, I hope, more clear that the contacts are important. So the way how to do the contacts with your molecules is fundamental. A nanogap is defined as a structure with a gap between the two electrodes of less than 10 nanometers. You can imagine if you want to introduce your molecules and the length of your molecules, we will see, depending on the application, is from 1 nanometer to 10. Also, if we talk about sensors, and so we pass to bigger molecules, to larger molecules, we can reach also larger dimensions. But it's important to build breaks, to build gaps inside the electrodes of as most as controllable dimension. And this, now I can think that you already start to have idea of where we can use these nanogaps, mainly in nanoelectronics, because they will help us to build our new nano devices for going further, to advance from what the technologies we have now, that mainly is the CMOS technology, and they are also useful for having for using them as sensors, because if I create a gap of a dimension of a molecule that I want to detect, it's clear that I can detect the presence of the molecule. Also because we have seen, and we will see some AFM images, in the gap there is a sort of good point of lower energy where the molecules have a higher probability to go and to stay inside. And so, as you see, here we have our two electrodes. Here we continue to call them source and drain, but I told you, if you want, you can also a little bit leave out this concept of source and drain, and here inside we put our molecule. In literature and in the several applications now that you can find around the research in the world, there are mainly two possibilities to build them. One is to build them vertically. So in this case, I took these slides from a very interesting seminar made by Professor Lugli of University of Munich, where you see here you build a multi-layer structure, but at the end, for our purpose, the point is here, where you create, doing an etching, a standard etching process, you etch if the layer of the gallium arsenide layer, you see here the point here, you etch the gallium arsenide layer for having here the gap vertical in which you can insert your molecules. You can do them also horizontally. In this case, one of the interesting applications is this one, where you create mechanically your gap. So, using a piezo actuator on the bottom, you can press up to break with the nano dimension, your in this case, you see, you have a wire in which you create the break, okay, pushing from the bottom with your piezo actuator. And in this application, they reach about 100 and 250 nanometers. So they started to use wires of this dimension, the width. Okay, the width of a wire is about 100 and 250 nanometers. What we do here in Politecnico, we are producing horizontal nanogaps, and we produce them using electromigration. This means that electromigration was, and it is a problem in microelectronics because it breaks the wires inside the chips. In this case, we exploit it because inserting the current inside the gap in a controlled manner, we can break the wire. In fact, here you have some example. Here you have a wire in which, doing a good control of the process, you can break it, obtaining the nano distance between the two gold electrodes. And it is, you can imagine, a very simple and low-cost technique. Simple means I'm working on it, so I can tell you, not simple in doing it and obtaining the result, because we are studying this problem from almost 2 years, because the problem is not to create big holes, but to create small gaps, so it's very important, the control. But after that you have found the good parameters of your process, at the end the instrumentation that you need is not so complicated. Okay, now I gave you the starting points and starting concepts from which we can now leave a little bit the introduction to the problem and start to think about molecules. The molecules that we use inside our electrodes for building these new nano devices are mainly hydrocarbons. Hydrocarbons are compounds mainly based on hydrogen and carbon atoms. They are classified in 2 different classes. They are classified in saturated and unsaturated hydrocarbons. The saturated hydrocarbons are named alkanes, and the structure of alkanes, this is an example of a pentane molecule. You see, they are open chain, okay, made of carbon atoms, the gray ones here, and the hydrogen atoms around of hydrogen, so they build these chains. And in this case, one important point to remember is that each carbon, the hydrocarbon, has the maximum number of hydrogen atoms that we can have per carbon atom. This is because each carbon has a single bond to the other carbon atoms. So it means that he has one, you see, in this case, one to this carbon, one to this carbon, and you see the valence of carbon is 4, so the other 2 are completed by 2 hydrogen. You see, 2 hydrogen atoms. This in the left and in the right, there is no carbon atom here, so the valence is completed by another hydrogen atom. A general formula of alkanes is CnH2n plus 2. Which are the characteristics and the properties of alkanes that we want to understand for having the possibility to use them in our structure. At the end, they are almost isolants, so they have a very low conduction, and you already had some concept talking about the benzene, and we will go a little bit in detail in the benzene molecule, because the possibility to have an exchange of electrons inside your chains, inside your molecules, it is based on different structures. So, in this case, to have this long chain means that we do not have a very high conduction. They are also used for some purposes, and in this case, I introduce you the concept that the thiol, so you see here, you have this is a decane, an alkane made based on 10 carbon atoms, so it's a decane, and in this case it is a decane dithiol, means that on the left and on the right you have 2 sulfur atoms that make the thiol bonding that is a very strong contact with gold. So you can imagine we will find these thiolated molecules everywhere, and we will find almost in each of the molecules. We will analyze the possibility to have a bonding between the molecule and the gold electrodes using thiols. Just let's start to put down some numbers. We can say that alkanes have a HOMO-LUMO energy gap of about 8 electron volts, and now we will compare this number with the other molecules that we will analyze during this lecture. The unsaturated hydrocarbons are hydrocarbons in which the carbons between them have more than one bond, at least in one place, one or more than one bond, and we have the alkenes that in which the carbons have one or more double bonds between them, and the general formula is CN on H, CnH2n, H2n. We have also, and here I show you as example, you see an ethene molecule where you see here we have a double bond, or a propene molecule, you see here the double bond between the 2 carbon atoms. We have the alkynes. The alkynes are hydrocarbons in which we have a triple bond, at least one or more triple bonds, and you see you have here a propyne where you have also a chloride on this chlorine in this position, and here is a pentyne where you have here the 3 bonds. Here in the propyne the 3 bonds are here. So this is why these 2 molecules are alkynes. And the general formula of them is CnH2n minus 2. Let's pass to the most interesting structures for us, most interesting hydrocarbons, that are the cyclic structures. The cyclic structures are named, we can have cycloalkanes, so sort of connection between the 2 ends of an alkane, so you build these alkanes. But more interesting even are what are named the aromatic hydrocarbons, or arenes, that they are aromatic ring where you have an alternation, and this is one of the key points, of double and single bonds between the different carbon atoms. And I show you here some example. The benzene, we will go in detail soon in this molecule. The toluene, you see, naphthalene and other. You see, you have these rings with single, here for example, double, single, double, single, double, and benzene has this structure. Okay, so the arenes or aromatic hydrocarbons. Benzene. Professor Piccinini already told you and examined and analyzed the structure. I just want to recall some points. The formula is 6,6H6, and the benzene molecule has this alternation in the C double and single C bonds. And the special property of benzene to have what you have seen, these pi bonds inside the structure, has a strictly, of course, relation with the distance you have between carbon and carbon. In fact, the distance is in the middle between a single bond and a double bond. This means that effectively, we cannot say that between two carbons we have one bond, but we cannot also say that we have two bonds. We have a situation in the middle, and this is the key point. The key point, as you have seen, becomes from the fact that you have these sp2 orbitals between carbon and hydrogen. On the plane between the C atoms, you have sigma bonds. The p orbitals that are perpendicular to the plane of the ring are interconnected together using these pi bonds. And these pi bonds generates a sort of resonance structure in which you have two equivalent structures that are in resonance. One, you see, with the double bonds in this direction, and the single in these positions, and the single in the others, and the complementary, we can say, situation. These bonds create this sort of circle, because again, I told you, the distance is in the middle between one and two bonds, so it means that they are not one, not two, but instead of having separated orbitals here, at the end, the final orbital structure of your molecule is a ring inside, and now we have the key point, the electrons can move around. So, you have this resonance becoming from this hybrid situation, where the electrons can move. And so you have the localized electron that generates a sort of cloud around the ring of benzene, and if they can move equal, we can easily have a current. They are ready to move and to give us the current that we are looking for. So, the benzene molecule is the perfect candidate for us to become the basic brick of our molecular wires. In fact, for example, I give you here, and now we will enter in detail soon of different families of molecules that we can build for our applications. Here I show you, here you have this chain of three benzene rings. Here you have a thiol, so the sulfur on the left and on the right. And so if you put this molecule inside two gold electrodes, you can generate a current inside your molecule and inside your M metal, M molecule, M metal structure. Which are the characteristics of the currents that we have inside this structure? We have two possibilities, and I will spend a few words later also on it. We can have the possibility to have a current based on a tunnel effect. So you have your electrons that passes inside through a barrier, and so you have your tunnel current. But with these molecules, we can also have hoppings, so electrons that takes enough energy to jump, we can say, from one ring to the other to move inside our molecular wire. Okay, now these are the basic concepts: benzene, rings, and delocalized electrons. Let's go in details in showing you which are the most used families of molecules we can have. The first family is what is named the oligophenylene molecules, where we have more than 3 rings of this basic structure that is based on phenylene, so a benzene without 2 hydrogens atoms, this one, plus an ethylene, so a chain based on 2 carbons that have between them 3 bonds, and so they have the 4th bond free on the right and the left for having the interconnection, the bond with the outside world. And this is a derivation from the ethine, because the ethine is based on this molecule plus the 2 hydrogens on left and right. So we exploit the fact that these chains are named conjugated chains because of these delocalized electrons that we have in the benzene, and so we can create, as you see here, which is OPE with 3 benzene rings, here the ethylene in the middle, and here you have sulfur plus another group. The other group is acetyl. Acetyl is not needed for the functionalities of the device, but the thiol group are very reactive. So you cannot have your molecule with the thiol groups free to react with outside world, as you have immediate reactions. And so you protect these thiol groups using acetyl. Before having the bonding of your molecule on your gold electrodes, you use some chemical solutions for detach the acetyl in place close to the electrode, so you put out the acetyl, so in this case the thiols are ready to attach, to bond to the electrodes. Thanks to these delocalized electrons, the OPE are good conductors, and you see the HOMO-LUMO gap, in this case, you remember for the alkane was 8, here is 3.5 electron volts. The second family that we analyze are the OPV, so the oligophenylene vinylene. These are based as basic repetitive structure on, again, phenylene, but here we have the vinylene. The vinylene is obtained taking out 2 hydrogen atoms from the ethene. So we can build chains based on this structure. Again, you see you have the phenylene, the vinylene here. This is a chain again based on 3 rings, and again the sulfur, so the thiolated bond, and here the acetyl for protection. One interesting property of OPV is the fact that thanks to the vinylene structure, they are more planar. And the triple bond of the OPE, triple bonds of the OPE, blocks this alternation of single-double bonds. That is the key of having this delocalization of electrons. So we can conclude that becoming from these 2 properties of OPV, the OPV are more conductive than OPE. And in fact, you can immediately see from the HOMO-LUMO gap that is about 3.1 electron volt, and we can say that having similar structure, having similar lengths, so number of rings of OPV or OPE, we obtain at 1 order of magnitude of increase in conductance. Last but not least, the oligothiophenes. Oligothiophenes are molecules based not on benzene, but on a similar structure, that is the thiophene. The thiophene is a ring in which you have 4 carbon atoms and 1 sulfur atoms, all bonded to create this basic structure that is a ring. And again, for the thiophene, the game, we can say, is the same. So we have again the p orbitals, we have the pi bondings, and so this structure has again a ring where we have the delocalized electrons. And so in this case, I show you this ring with some other molecules and alkane chains. In this case is a molecule that I show you because it is the one that we will use doing some analysis of some experiments that we had here, and we use this molecule, so this oligothiophenol chain. And at the end, we can say that this structure is even more reactive than and stable than the benzene molecule, and so we obtain again an increase in conductance. Just to summarize what we have seen up to now, we have now the possibility, we have as a mind the alkane, so you see the length, and the length is important because we know which must be the dimension of the gap between, of the distance between the electrodes that must use the molecule. So you see we are talking about 10 to 20 Armstrong, and here is the HOMO-LUMO gap, about 7-8 electron volts. OPE are a little bit longer. Of course, we can also, the basic structure, but we can also create long chains, but it is a point that we will touch in the next lecture. The length of the chain, it's strictly related and is proportional to the conductance, to the current we can obtain in our device. So starting from the basic OPE, so with the 3 chains, 3 rings, the distance is about 19 Armstrong with a 3.5 gap, 20 for the OPV, we are having 3.1, and the third thiophene, so for doing a comparison of same structure, same length in 3 rings, we take 3 rings of thiophene. So the third thiophene, the length is 1.4 nanometers, so 14 Armstrong, and the energy gap, the homolomo gap is 2.9 electron volts. Now I quickly show you some molecules that we found in literature, showing that I just touch some basic example, but these molecules can be changed, and we will see soon the possibility to create a sort of p-n junction between molecules. So they are also changed, adding some external chains or some other molecules for giving them different properties. So you see here some OPE, so some different OPE, types of OPE. Again, here we have other OPE, or here we have, for example, a third example of vinylene, so OPV, so you see with different, well, usually the termination you see are again sulfur and acetyl, and in the middle you have these different molecular wires. I did not talk about ferrocene, that is another interesting structure to be used in our molecular wires, and this here you have some examples. The interest of these molecules it raised in the last years, and in fact now I just give you an example of a catalog. In this case we are talking of Sigma Aldrich, where you can find and buy directly these molecules ready to be used in your nano devices. And in the catalog, I took this example because it's interesting, because you see you can find p-type chains, so sort of p-type semiconductors, and so you have here you see here the thiol groups and the different structures having different mobility, different characteristics, and also you have the complementary structures, so the n-type structures, n-type molecules. So starting from this, you can, I give you this as first example. We will have later some lectures specific for giving you coverage of the possibilities in creating devices and applications. So starting from these basic molecules, you can set up a p-n junction, so a diode based on these molecules, where you put a molecule that can be the donor, the molecule that can be your acceptor. You put in the middle this R group that at the end is an insulating group, that is the barrier between the P and N molecule, and so you obtain at the end the structure in which you have your bands, your band gaps, and so on, for thinking to build inside the 2 electrodes with a chain of different molecules your first, we can say, p-n diode based on molecules. In the next lecture, we will pass to analyze the possibilities that we have in changing conductance in our structure, changing length, rotation of the molecules. So we will analyze together which are the characteristics of our molecular wires that influence the conduction and the current we can have in our devices.